Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over how to evaluate indefinite integrals using the fundamental theorem of calculus part 2. This topic is covered under AP Calculus AB and Calculus 1. There are 4 practice problems at the end of this presentation, so don't forget to try those out in order to demonstrate mastery. If you'd like to gain access to our U Substitution playlist, the entire calculus course, worksheets, formulas, and other valuable resources, just take a look at the description below. Alright, let's go ahead and take a look at the first example. The task is as follows. We are to evaluate the given integrals. Okay, so evaluate. So let's say we are to evaluate, number 1, want to evaluate the integral of sine x divided by the square root of 1 plus cosine x. We're going to be using the U substitution method here. To get us started, let's go ahead and write down the formula that's going to govern our problem solving process. Okay, so the formula for U substitution is as follows. So you have the integral of a composite function f of g of x times the derivative of the inner function g prime of x dx. This can be rewritten using U substitution as the integral of f of u du. Think about this as a reversal of the chain rule. Okay, this happens where u is equal to the inner function g of x. The big advantage of the U substitution method is that it enables you to rewrite complicated integrals in a simpler format that enables easy integration. Okay, so let's take a look at how this works with this example right here. So we have to evaluate the integral of sine x divided by. Now, one thing to keep in mind is the way that you express your integral makes it very easy to carry out this U substitution process. Now, what I'm going to write this integral as is as the composite function times the derivative of the inner function. Okay, so I'm going to separate it. So we have the integral of the composite function, which is 1 over the square root of 1 plus cosine x. Is a composition of rational, radical, and a trig function. And then we have the other function, sine x. I'll put that to the side, sine x dx. Okay? Alright, the benefit of this is it makes it easy to identify what goes where. I will start with the inner function for my u, so we're going to have 1 plus cosine x be u, because that's the biggest function that I can select. That upon differentiation, I end up with a multiple of the second function. Okay, so u is 1 plus cosine x. So we're going to go ahead and differentiate both sides with respect to x. So du dx is equal to the derivative of 1 is 0. The derivative of cosine is negative sine x. And now we want all the x's on the right and the u on the left, so multiply both sides by dx. So you have du is equal to negative sine x dx. Okay, you don't have to do this intermediate step. You can just jump from u to du equals negative sine x dx. Okay, this step is just to show you exactly what's going on. Alright, so now we know what du is. Du is negative sine x, and we have this other portion right here. So the question is, do we have a perfect match? If you look at what we have here, we have negative sine x, and over here we have sine x dx. Do we have a perfect match? The answer is no. We have a mismatch. What's the mismatch? The mismatch is that there's a negative with du, and this function here does not have this function doesn't have a negative. So we have to rectify that difference before we can make a clean substitution. So to fix that problem, we're going to proceed to divide both sides by negative 1. Okay, so what's that going to give us? We're going to have the negative du. Let me fix my colors here. Negative du equals sine x dx. Now we have a perfect match. You see sine x dx matches perfectly with sine x dx here. Well, what does that mean? It tells us that we now have the freedom to replace this entire component right here with negative du. Okay, so always know exactly what's going where first before you carry out your use substitution so you don't make errors. Okay, so now we're going to carry out the use substitution. This entire integral here becomes the integral of 1 over root u times negative du, which can be rewritten as you factor out the constant, which is negative 1 or just negative, integral of 1 over root u du. So this illustrates the power or the beauty of the use substitution method. This complicated integral has been rewritten as something really nice here. Okay? Alright, so what integration technique can we use for this? It's not that obvious, so we might have to rewrite this to make it doable. So how about we rewrite it using the properties of exponent as the integral of u to the negative 1/2 du. Okay, we have the negativity because we're reciprocating, and we have 1/2 is just a rational exponent representation of square root. Now we can integrate using the power rule. Okay, so hopefully you remember what the power rule is. Let's just, so let's do it. We're going to apply the power rule here. So the integral of u to the 1/2 du is going to be applying the power rule u to the 1/2 plus 1 divided by 1/2, no, negative 1/2 plus 1 divided by negative 1/2 plus 1. Okay? So we're going to carry out the subtraction. Oh, let's not forget the c. So plus c. Okay, and then when we simplify, this becomes u to the negative 1/2 plus 1 is 1/2 divided by 1/2 plus c. Alright, so we have a compound fraction here. We can rewrite this. Just keep change flip or multiply the numerator by the reciprocal of the denominator. So we have 2 times, let's not forget the negative here. We have a negative here, and then we have a negative here. Okay, so we now have negative 2 times u raised to the 1/2 plus c. Okay, so are we done with the problem? The answer is no. One thing about use substitution is that, first of all, you carry out a substitution first, and then when you're done integrating, you resub. Okay, so here we did a substitution, sub, and then when you're done integrating, guess what? We're going to resub. What does that mean? We're going to resubstitute what we substituted out back for u. Alright, so our initial substitution was, we said let u be 1 plus cosine x. We have now integrated nicely. Now we're going to resubstitute what u is, which is 1 plus cosine x, back into the antiderivative or the integral. Alright, so negative 2 u to the 1/2 plus c becomes negative 2 times 1 plus cosine x raised to the 1/2 plus c. Okay, you can write this as in this format using rational exponents, or you can say negative 2 times the square root of 1 plus cosine x plus c. Alright, so whichever format you write it, that is correct. Ladies and gentlemen, this is the answer to question number 1 on how to use the U substitution integration method. Alright, so we have a question for you to consider. Now, when we had it set up as the integral of 1 over root u, how easy was it for you to evaluate this integral? Was it obvious that it should be rewritten as this, or were you thinking about another method to evaluate this integral? Let us know in the comment section below how complicated this particular step was for rewriting this integral as a rational exponent. Alright, let's take a look at question number 2 on how to integrate using U substitution. So let's say you want to find the integral of dx over cosine square 2x. Okay, we're going to do this using the U substitution method. Now let's start off by rewriting what the formula is. Hopefully you remember. Let's just refresh our memories again. The formula for the U substitution method is the integral of f of g of x times g prime of x dx equals what? The integral of f of u du, the reversal of the the chain rule differentiation method. Okay, this happens where u is the inner function g of x. Alright, so we're going to apply that here. So first thing we're going to do, as we did in question number 1, is we're going to rewrite this in a way where it's easy for us to identify what the inner and f of g of x are. Okay, the inner function and f of g of x. So let's go ahead and separate it. We want to write down the composite function, which is clearly 1 over cosine square 2x times the other function, which is just dx. Okay? Now, can you see what the inner function is here? Well, 1 over cosine square x is not an easily recognizable antiderivative or derivative. So what we're going to do here is, how about we write this in a format that's consistent with a known derivative? Remember your identities. You remember what 1 over cosine theta is? So 1 over cosine theta is what? Is a reciprocal identity. 1 over cosine theta is equal to secant theta. So that follows that 1 over cosine square theta is secant square theta. Okay, so using our reciprocal identities, we can rewrite this as rewrite this integral as the integral of secant square 2x dx. Now that looks much better. Okay, we know that secant square is a known derivative, so we can easily now identify what our inner function is. Our inner function here is going to be u. Okay, so we say u is 2x. Then what is du going to be? We differentiate both sides with respect to x. So we have du dx is equal to 2. Multiply both sides by dx. You have du is equal to 2 dx. Alright, so now do we have a perfect match for our substitution? Let's take a look at what we have here. We have du is equal to 2 dx, and over here we have dx. Do we have a match? The answer is no. We have a mismatch. Okay, why? Well, we have 2 dx here, and this is just dx by itself. So we need to have an identical match on the right side of our equation in order to be able to carry out the substitution. So in order to rectify the difference, what we're going to do is just simply divide both sides by 2, since we cannot have anything attached to dx in order for it to match this, the lefts to match this component perfectly. Alright, so when we divide both sides by 2, we have du over 2. Let's change colors. We have du over 2 is equal to what? Du over 2 is equal to dx. Bullseye. That's exactly what we want, because if you notice, now we have a perfect match. Now we can call this component right here du over 2. This is a very, very important step. You must know what u and the du or its multiple is before you carry out your substitution to avoid making errors. Okay? Now, what are we going to do? We're now going to carry out the substitution step. Okay? Substitution. Now, substitution step is as follows. We're going to have, what are we going to have? We're going to rewrite the integral as the integral of secant square, not 2x, but secant square u, and then replace the x with du over 2. Okay? Now let's factor out the 1/2 multiple there. So factor out 1/2. So we have 1/2 times the integral of secant square u du. Alright? Whenever possible, factor out multiples or coefficients or negative signs from your integrand, because it simplifies the process considerably. Alright, so remember what the antiderivative of secant squared theta is, right? If you integrate secant squared theta, you end up with tan, because we know that the derivative of tan theta is secant squared theta. Let's just write that down just as a refresher. If you differentiate tan, you get secant square theta. Okay, so when you integrate, you have tan theta plus c. So let's use that reversal of the differentiation rule here to integrate, and we're going to have 1/2 of, instead of secant squared theta, the antiderivative is tan u. Remember, after you integrate, the integral symbol, this h symbol, and the du go away together. Okay, and don't forget your plus c, because this is an indefinite integral. Are we done? The answer is no. Whenever you substitute and integrate, you have to carry out your resub step. You have to resubstitute what you substituted out to enable your integration. So our substitution was u equals 2x. Now we are going to have to resub. What does that look like? The original problem, the answer that we got was 1/2 tan u plus c. Now we're going to resub. We're going to take our u and replace it with the original substitution we carried out, which is now 1/2 tan. Instead of u, we have 2x plus c. Ladies and gentlemen, this is the final answer to question number 2 on how to integrate using the U substitution method. Alright, we'd like to get your opinion on a question. On a scale from 1 to 10, how do you like your differentiation rules for trigonometric functions? On a scale from 1 to 10, how do you like your differentiation rules for your trigonometric functions? Sine, cosine, tangent, secant, cosecant, cotangent. Give us your response in the comment section below and tell us why you selected that answer. Alright, now let's go ahead and take a look at question number 3 on how to integrate using the U substitution method. So let's say we want to integrate, evaluate the integral sine of 2t divided by 1 minus cosine 2t dt. Alright, to get us started, let's go ahead and refresh our memory on what the formula is for integration using U substitution. Okay, so the formula for integration using U substitution is as follows: the integral of f of g of x times g prime of x, we went over this in numbers 1 and 2, so this is just a refresher for you, is equal to the integral of f of u du. Just remember that U substitution enables you to express complicated integrals in a much elegant and easy to integrate fashion. Alright, let's go ahead and do it here. So first things first, what we're going to start off with is rewriting the problem in a way where it's easy for us to identify what the composite function is and the derivative of the inner function. Okay, so we executed these exact steps in problems 1 and 2. We're going to do it again here. So what we're going to do is separate it. Let's write the composite function first in harmony with the formula that we have here. Alright, so the composite function, which is a composition of a rational function, a linear function, and a trigonometric function, is 1 over 1 minus cosine 2t, and then times the other function, which is the derivative of g of x. Okay, the derivative of the inner function. So we have sine 2t dt. Alright, so let's go ahead and identify what our u is first. So our u for U substitution is the biggest innermost function that results in sine 2t or its multiple upon differentiation. Okay, so I could have selected cosine 2t, but there's a 1 there that if I add it on and differentiate, I will still get exactly the same result. So the bigger the function, the better, the easier the substitution is. You want to substitute as much as possible so it looks elegant. Okay, so if that is our u, we're going to say u is 1 minus cosine 2t. So we're going to differentiate both sides with respect to t. So du dt is equal to derivative of 1 is 0. The derivative of cosine is negative sine. So if you multiply that with this negative right here, it becomes positive. So it's going to be positive sine. Derivative of the outer evaluated at the inner, chain rule, times the derivative of the inner. The derivative of the inner function is 2t prime, which is 2. Okay? So there you have it right there. So that's du dt, so multiply both sides by dt, so that's du is equal to 2 sine 2t dt. So the question now is, do we have a clean substitution? Take a look at what we have here, sine 2t dt, which we want to substitute also, and over here we have 2 sine 2t dt. Do we have a match? The answer is no, we do not have a match. Sometimes we have a match, sometimes we don't. In this particular case, we do not have a match, so we have to carry out some arithmetic operations to make sure that they match. Okay, so what are we going to do? We need to address this coefficient here, since this derivative of u doesn't have a coefficient, derivative of g. So what we're going to do is divide both sides by 2 to fix that problem. Divide by 2. So we now have du over 2 is equal to sine 2t dt. Ladies and gentlemen, we have a perfect match. Check this out. Sine 2t dt, this matches perfectly with what we have on right here, sine 2t dt, and that tells us that this is du over 2. Okay, now let's go ahead and make our u substitution. When we carry out our u substitution, we're going to have this complicated integral is now going to become the integral of 1 over u for this portion, and then the derivative of g prime is going to be du over 2. Okay, let's make it look pretty. Factor out that divided by 2 or multiply by 1/2. Factor that out. So we have the integral of 1 over u du. Do you see the power of the u substitution method? This complicated integral right here has completely been simplified into this elegant looking integral, which is very easy to integrate. So the antiderivative of 1 over u is the natural logarithm of u. So this becomes 1/2 of the natural logarithm of the absolute value of u plus c. Are we done? The answer is no. We carried out our substitution step here, and guess what we do after you integrate? You have to resub. Alright, you resubstitute what you substituted out. So if we carry out our resubstitution, the answer that we got, 1/2 times the natural logarithm of the absolute value of u plus c. We'll take that u out and replace it with what it originally was, which is 1 minus cosine 2t. Your answer will be 1/2 times the natural logarithm of the absolute value of 1 minus cosine 2t plus c. Alright, ladies and gentlemen, that is our final answer. Let's just write it again. Final answer for the problem is 1 minus cosine 2t 1 minus cosine 2t absolute value natural logarithm. Alright, so there goes the final answer for question number 3 on how to use the u substitution to carry out the integration process. Alright, we have a question for you on this problem. There's a common mistake that most students make when integrating this particular integral. They try to use the power rule technique. They rewrite this as the integral of u to the negative 1, and they try to use the power rule, and it ends up being undefined. So the question is, did you think of using the power rule to integrate this, or were you able to remember that the integral of 1 over u is ln absolute value of u? If you remember to do it, or if you forgot, just let us know in the comment section below so we can see how good you were at evaluating this special integral 1 over u. Alright, let's take a look at question number 4 on how to evaluate integrals, indefinite integrals, using the u substitution method. So let's say we're to evaluate the integral of e to the 3x divided by e to the 3x plus 1 dx using the U substitution method. Alright, so let's get started by refreshing our memory on what the U substitution formula is. So this is the fourth time you're seeing it. We went over it in examples 1, 2, and 3, so you must be a master at it right now. So the formula is as follows. The integral of f of g of x dx, f of g of x times g prime of x dx is equal to the integral of f of u du. Just think about it as the reversal of the chain rule for differentiation. Okay, so the power of the U substitution is that it enables you to rewrite complicated U substitution problems in a format that's very easy to integrate. Okay, so let's go ahead and attack the problem. So we have the integral of e to the 3x over e to the 3x plus 1 dx. Now, one good practice, as we did in problems 1, 2, and 3, is to write it in a way where it's easy to identify what the composite function f of g of x is and what g prime of x is, the derivative of the inner function. So we're going to rewrite this problem as the integral of 1 over e to the 3x plus 1, this is the composite function, times e to the 3x dx, the derivative of the inner. Okay, so let's go ahead and identify what u is. So this inner function right here is u because when you differentiate that, you end up with a multiple of this. Let's show that on the side here. So we say u is e to the 3x plus 1. When you differentiate this, du dx, du dx, du is going to be, now we're going to use a chain rule here because we have a composite function. Derivative of the outer function is e to the x, or e to the x, or e to the u. So the derivative of the outer evaluated at the inner is e to the 3x. And then we're going to multiply that by the derivative of the inner function, which is 3. The derivative of 3x is 3. Okay? Plus the derivative of 1 is just 0. This was du dx, so we multiply both sides by dx, so we have that. 3e to the 3x dx is what du is. Now, do we have a perfect match for substituting du? Let's see. If you look at what we have here, we have e to the 3x dx, and over here we have 3e to the 3x dx. Does it match perfectly? Sometimes it does, sometimes it doesn't. In this particular case, we have a mismatch, so we have to fix that problem. Okay? So to fix that problem, we're going to have to divide both sides by 3. So divide by 3. Because this component here doesn't have a 3 in front of the e. It doesn't have a 3 coefficient, so we can't have this right here. Alright? So that divides out, and that gives us du over 3 is equal to e to the 3x dx. This is exactly what we want. We have a perfect match. Check this out. We can now replace this entire component with du over 3. Very important. You want to know exactly what u and du or its multiple is before you carry out your substitution. Alrighty, so now we are going to go ahead and substitute. Let's do our substitution. This integral that we have right here is going to become the integral of 1 over u times du over 3. Let's factor out that du over that 3 on the bottom, so we have 1/3 times the integral of 1 over u du. Isn't this fantastic? Take a look at the original problem we have, and after the u substitution, look at what we have. This is really, really great. Now, what is the integral of 1 over u? We've confronted this particular integral in question number 3, and we talked about using the power rule incorrectly here. In this particular case, do you use the power rule or not? The answer is no, you do not use the power rule. For this particular integral, you're going to use the integration rule. The integral of 1 over u is the natural logarithm of the absolute value of u. Okay? So that's what the integral is. And don't forget the plus c because this is an indefinite integral. Are we done with the problem? We are not done. Remember, after you substitute and integrate, you have to do what? You have to resub. Okay, what you substituted out for you, you have to plug it back in. So we're going to carry out our resubstitution step, which will be the final step here. So the answer we got was 1/3 times the natural logarithm of the absolute value of u plus c. So when we resub, this is going to become 1/3 of the natural logarithm of the absolute value of e to the 3x plus 1 plus c. And there goes your final answer. Okay? Alright, now we have some practice problems for you to try out to demonstrate that you have mastered the art of integration using U substitution. Alright, so let's have you go ahead and try these. Task is as follows: you to evaluate the given integrals. So for question 1, what if you were to evaluate the integral of secant square x over the square root of 1 plus tan x? Number 2, what if you were to evaluate the integral of dx over sine squared 3x dx? Yeah. Alright, number 3, what if you were to evaluate the integral of cosecant square 4t divided by 3 plus cotangent 4t dt? And then lastly, number 4, what if you were to integrate e to the 5x over 2 e to the 5x plus 4 dx? Alright, so what I would like you to do, go ahead and pause this video presentation and attack these 4 problems. When you're done, click back on the play button and then you're going to see what the answers are. Alright, so hopefully you had a chance to try out these 4 problems. The answers are as follows. For question number 1, the answer is 2 times 1 plus tan x raised to the 1/2 plus c. Number 2, the answer is negative 1/3 cotangent 3x plus c. For number 3, the answer is 1/4 times the natural logarithm of the absolute value of 3 minus cotangent 4t plus c. And for number 4, the answer is 1/10 times the natural logarithm of the absolute value of 2e to the 5x plus 4 plus c. Okay? So we'd like to know how well you did on these practice problems. Did you get 100%, 75, 50%, 25%, 0%? Let us know in the comment section below. And if you have any questions or any clarifications that you like, go ahead and place it in the comment section. We'll be glad to address those.